Welcome back for another screencast on material science. Today we are going to talk about sputtering of atoms in 2D materials. And the sputtering takes place by transmission electron microscopy, and more specifically it is the electron beam from the microscope that does the job of sputtering. So the objective of this 40-ish minute screencast is to provide you a fundamental understanding of the processes that lead to the sputtering. So before I start, I have to say that I have to make some important acknowledgement. Most of the work I'm going to show you today is actually the result of Anthony Yoshimura's thesis, final project on his thesis, and in particular this 2023 nanoscale paper that's listed in the bottom there, so you can have more information about this project in that paper if you're interested in more detail. I'm going to try to avoid talking too much about equations, so I will show a few equations, but I will mostly describe them. If you want to go in depth about the theory, I invite you to go to the reference provided in the previous slide. So the outline of this presentation will be as follows. I will first provide you a couple of slides explaining what is sputtering by transmission electron microscopy, explain why the classical approach failed to explain quantitatively the cross-section of sputtering. We'll talk about temperature effects, and after that we'll look into why quantum theory is important to understand quantitatively what's happening during the sputtering process. And finally, I will compare this with some experimental data, and hopefully this will wrap up this presentation. And I hope that by the end of this screencast, you'll get a better understanding and a better appreciation of what's happening under the microscope. So let's talk a little bit about sputtering first. Personally, my first foray in this area was this work almost 15 years ago with the work of Millie Dresselhaus at MIT. What we were interested in here, or in fact the experimentalists were interested in, is to start from the structure on the left-hand side in panel A and see how the edges of this graphene flake could be straightened up or cleaned out as shown in the cartoons, in the red cartoons on the leftmost and rightmost part of this picture. And so what was happening there is that Joule heating was applied. Joule heating is basically the idea of having a large current go through the structure, and that current would help reorganize the atom. But it turns out that this could only happen under the microscope, in the sense that the additional energy from the electron beam was necessary to displace atoms. So there was a number of sputtering, migrations, and other effects that made it such that the microscope could be used to controllably move atoms around. So that was the first idea of the sputtering in my personal scientific career that I was involved in. The second one was related to phosphorine. So phosphorine is an example of a two-dimensional material. The structure looks like this. And it's an interesting structure seen from the top because it's not isotropic. So if you look at the x direction or the y directions, you have two different structures. So it's an interesting thing. And in fact, if we could cut it, for example, in this direction, we could create a ribbon, which is a particular direction here with a zigzag edge. Or if we cut it the other way, we could create a ribbon, which is an armchair edge. And so they are non-equivalent because the crystal is not isotropic. So that's interesting, and this is a structure that was of interest, that started to be of interest about 10 years back. There's been a lot of work going on in phosphorine. This talk is not about phosphorine, but phosphorine has been a little bit lost a little bit of hype simply because it's easily oxidized. It's not as stable as some other 2D materials. But that would be another screencast to talk about phosphorine maybe at another time when I have time to add to this YouTube channel. Okay, so the idea is that how can we actually shape the edges using a microscope? And this is actually schematically how you do it. So you see the gray cone there actually represent the electron beam. This is a picture from the group of Maria Derndic at UPenn. So these were the experimentalists to work on this while we did the theory. So what they did, they created those spores, so they actually bombarded phosphorine, starting from phosphorine in figure A. And then the idea there was to start to create a pore. And you see that as you go from B, C, D, and so on and so forth, the pore is getting bigger and bigger as there's more electrons being thrown in the material, and the material is subjected to sputtering. So what we see here is that repeatedly, repeatedly we find that the pore actually grows elliptically, and this is actually a demonstration that we have a non-isotropic material. If you're doing pore in like MOS2 or graphene or things like that, usually on average the pores are a little bit more spherical, simply because you have the isotropy. In any case, the point here is that you can create those pores using sputtering. And when you do that and you create pores that gets closer and closer to one another, like for example in B, what's left, the material that's left in between, actually looks like a one-dimensional ribbon, which was the objective that we had. Of course, if you go too far, like in C and D, you have to break the bridge between the structure. So more specifically, if you have a ZIGZAG nanoribbon here, you can actually start to make it cleaner and cleaner and nicer. You have a pretty much perfect constriction, and you can thin it more and more through sputtering until, of course, you break the junction and you get you basically lose your material. So this is, during all this process, it's a matter of sputtering. So how the electrons bombarding the material with electrons will actually get rid of the atoms. I will also notice in this picture this was done under the aberration corrected microscope, so you actually see the atoms as well. You can do this in the other direction. I'm not going to go too much in detail, but you can go that in the other direction and create also an armchair structure. So essentially the cartoon I was showing you a couple of slides ago, we were able, with of course the experimentalists at the University of Pennsylvania had a big part of this because they actually did it, but we were able to do what we wanted to do. Now, one thing that comes across a lot in two-dimensional material is not so much those big changes, but smaller changes, like creating vacancies in MOS2. I mean, vacancies have a lot of interesting features, including in qubits, including in catalytic properties and other photoluminescence properties. And so this is an interesting thing to create vacancies. So let me just spend a few seconds explaining here this material on these two pictures on the bottom of the slide. This is MOS2, but actually all the structure that will be metal dichalcogenide that I'm going to talk about today have the same structure. So on the left-hand side is sees from the side, and it's a bilayer, and the right-hand side is seen from the top. And what happens there is that you have molybdenum shown in green and sulfur shown in blue. So when you have sputtering, the idea is that you have an electron beam coming to the material, and this is a sulfur at the bottom that's going to be sputtered. MOS2 is not, molybdenum is not going to be sputtered so easily, simply because it's more tightly bonded to the material. So the first atom that will be sputtered has sulfur. And so when you create one vacancies like this, you can see it under the microscope, and the group of Komsa there in the Fizdrev letters in 2015 were able to observe those single vacancy, and they look like those triangular pattern that we see. Now, again, in another project with a group at UPenn, we were interested in seeing if we can quantify the number of defects that we have in this material. And usually, experimentally, the way people calculate quantitatively what's happening in the material, they take a microscopic image and they essentially count the number of defects. Used to be that, and it's still very much the case, that people count it by hand, that they truly look at the material, at the micrograph, and calculate the number of defects. Now there are machine learning techniques, pattern recognition, because pattern recognition is well adapted to machine learning methods that allow you to do the same. But it remains that in order to get the number of defects, you need to do an aberration corrected microscopy image, which is actually, of course, takes takes quite a bit of time. It also takes a very expensive equipment, like an aberration corrected microscope. So in this work there, we were interested in seeing, can we use a cheaper method to tell how many defects we have. And so a lot of work in my group is related to Raman spectroscopy. And Raman spectroscopy, we actually measure the frequencies of those particular vibrational mode. Just as an aside, there will be a 2-part tutorial on Raman spectroscopy in this YouTube channel sometime before the end of summer 2023, available here. Hopefully that will help those who are interested in that topic. But in the meantime, suffices to say that we have those particular vibrations that we see on the left-hand side. And it turns out that those vibrations have 2 of them, the E2G and the A1G. Actually, it's very specific to MOS2, or to any MX2, in fact, where M is a metal and X is a chalcogenide material. And experimentally, what happens is that it was found that the frequencies of those modes, at least the E mode, is very much dependent on the amount of defect. So what we did theoretically, using first principle calculation, we were interested to see, is there a predictive relationship between the number of sulfur vacancies and the peak shift. And indeed, that's what we found, so it's quite a while back, to see that one of the mode, the E prime mode, is actually more affected than A prime mode, and we can explain that from the force constant. And again, I'm not going to detail this too much because I want to get to the crux of this presentation, which is coming up in 2 slides. But the point is, it's important because now we can calculate the amount of vacancy, so in other words, the sputtering efficiency, if you will, as just using Raman, because these are the theoretical data and these are the experimental data. And the experimental data fit pretty well on the theory, which is always nice. You will notice that those curves, the experimental curves, do not start at 0, simply because most of those material do have built-in sulfur vacancy in them. It's actually very difficult to make a material without any vacancies at all. So you basically do not start from 0 when you create those vacancies under the microscope. Okay, so let's go into the understanding sputtering now that we have kind of a picture of what sputtering can do. And we are talking about cross-section. So I'm going to remind the audience what we mean by cross-section. It's always a good idea. So let's see what happens. So let's simplify this a little bit. We have the atom, which is shown in red, and we have an electron that's shown in blue. So the electron in blue is the electron coming from the electron beam, and it's moving to the right. Now, of course, this electron is going to be scattered by the atom, and by conservation of energy and conservation of momentum, the other atom, of course, is going to be deflected so that the total momentum is conserved. Now here, the arrow of the deflection is proportional to the momentum transfer. If that momentum transfer is too small, like for example here, for instance, the atom is not going to be displaced. So by displaced, we mean ejected from the material. Of course, it's going to be moved and go back, relax back to the crystal, but it's not going to be displaced in the sense of ejected or sputtered. Now, if the electron, the scattering if the impact parameter is a bit smaller, so if it gets a bit closer to the atom, then the deflection or the scattering is much important, and of course the momentum transfer is also much more important. In that case, we can actually have displacement. So that means that there are some conditions under which some condition for the electron, for the beam electron, for which there will be sputtering. And those conditions are all quantified by what we call the cross-section, so the displacement cross-section. So in this case, if you want just to look into the classical or the real space view of the cross-section, if the electron actually start from sigma naught, the surface sigma naught, it will be deflected. Of course, this displacement depends on the velocity, it depends on the energy, and the energy of the chemistry of the material as well, but this is the idea. And when people talk about understanding sputtering in anything, in material, they're really talking about finding what this cross-section is. So This picture should be pretty familiar to many people about the Rutherford scattering. This is very much the same idea here, which is really kind of a collision, classical collision type of thing. But we are going to go a little bit deeper than that. So the question we are really wondering is what exactly happens at the atomic scale. And again, this is a picture that's another view of the previous picture. Here I just showed the entire material. You have the electron coming from the top, the beam electron coming from the top, scattering with the red line. And then, of course, you have a sulfur atom that can be sputtered. By the way, I like this picture because it's really convincing that the atoms that actually sputtered are not the top layer, but the bottom layer. And I'm sure you can convince yourself of that if you were trying to do that for the top layer, it would be very difficult to sputter it downward. I let your imagination figure out what would happen if you were trying to sputter the top layer atoms. So we are interested in doing this. Now, before we move on, we have to understand that, of course, we have this process of sputtering, the atom being ejected, but we can also have another effect, which is called migration. And in fact, in what I showed you at the introduction of the screencast about reorganizing a material, migration takes a big role. Migration is the idea that when you have the energy from the electron, from the beam electron, can be used to move vacancies around. And I will actually go back to that at the very end of the screencast to show you that the energies that are involved in migrations are much smaller than for sputtering, and therefore, once you have vacancies, you do expect that you can use the electron beam to rearrange your material actually much more easily than it is to sputter atom. But in any case, the sputtering will be destructive, the migration will be non-destructive, it will be essentially rearrangements of your material. Good. Now that we know what we are trying to do, let's try to see about how we can when we see what happens during the actual sputtering thing. So to simplify, if the atom to be sputtered is part of the crystal structure, that means that it's at the bottom of a well. It is the bottom of the well. The forces are zero there, and it's basically stable. Now, if we want to sputter, the idea is to eject the atom from the well. And the energy that you need, so classically, energy conservation, thermodynamics tell us the energy you need to get there is the height of this barrier, which is called the threshold energy. So the displacement threshold energy. So if you were able to impart that kind of energy to the atom, it will actually be ejected and sputtered. Now, of course, we are providing energy through the electron beam, and the energy we impart is called here EC, which is a critical energy that you need. Now, very naively, you would think that so long as EC is equal to ED, we'd be in good shape and we would actually sputter. But it turns out, and I will show that some numbers in a minute, EC, if ED is about 10 eV, let's say, EC has to be in the hundreds of kilo electron volt. So we have many orders of magnitude, maybe 5 orders of magnitude difference between ED and EC. Simply because most of the energy of the electron is not transferred into the atom. And this is actually the difficulty, is that only a small portion of EC is useful for sputtering. So this is actually the answer we are trying to answer. This is the question we are trying to answer, sorry. The question we are trying to answer is what is the ratio between EC and ED, essentially. So let's try to do that. So let's go back to the picture that we have, and we are interested in the cross-section. Now, initially, it's very tempting to say that this is a classical effect. So we have really this classical effect of the billiard ball effect, if you will, where you have an atom knocking an electron interacting with another electron, like you would do in classical physics. And this work has been, this problem has been worked out, and probably many of you have worked it out in one of the undergraduate mechanics courses. And this is the displacement cross-section based simply on momentum transfer. And the two techniques, the two cross-sections that are known are, for example, the Rutherford one, which is for the atomic number larger than 20, or the McKinley and Feshbach one, which is for the smaller, lighter atom. So McKinley and Feshbach are the ones that are typically used for this. We call it the MF, sigma naught MF. And you see that in this equation, we see that the cross-section depends on the threshold energy, ED, and also the energy that's imparted by the electron beam, Emax, as well as the velocity of the beam through beta. Okay, let's not worry too much about the equation. The point is, Emax and beta are really parameters of the experiment. ED is an intrinsic property of the material. It's half difficult it is to remove an atom from the material. The good news is that we can calculate ED, and ED will be the energy that we need to impart to an atom for it to go away from the structure. And so these are actually kind of fun calculation to do in density functional theory. What we do, we start from the perfect layers, and then we do molecular dynamics, ab initio molecular dynamics. We give some energy to the atom in the form of kinetic energy, so initial velocity, and we hope that that energy will be enough for the atom to leave. So the first case, we are right under, and you see the atom comes back. It's going to come back here. It's just not enough, comes back. In the other case, actually it's just enough to go over the barrier. So you see, when we have that, we can calculate, we can modify that energy until we get the right energy. Good. So let's go back to this picture that I've already shown a couple of times. Now we know ED. We know we should be able to calculate sigma naught in the MF sigma naught from collision. And this is exactly what we do, and we end up with this kind of graph. Right? Just to summarize, this graph here will be the sputtering rate, so related to cross-section, for calculated in a situation where we have a scattering, so a momentum transfer between the electron and the nucleus. And when we look at this here, there are a couple of things I want to attract your attention to. The first one is that these the energy scales. So we just saw that ED is around 10 eV or something like that, 5 to 10 eV. While the energy that you need for the transmission electron microscope is the hundreds of kilo electron volts. So that's what I was mentioning a couple of minutes back. The energy difference is quite significant between the energy of the electron and the energy of the nucleus. This is not that surprising, really, because of the momentum transfer and the nucleus being so much heavier than the electron, of course. Okay, now we see, so that's also the first point. The second point is you see that it's much easier to sputter sulfur from MOS2 or WS2 than it is to sputter selenium from tungsten or MO. Now, this is not surprising because the bonding is just simply stronger for selenium, so you need to impart much more energy into the system, and also, of course, there is an effect of the mass of the atom. So this is all good, okay? So we see that the sputtering happens at lower energies, but once we can do that, once we start, we can actually have a higher sputtering rate. So everything is good and nice. Now the problem is with this model, it doesn't work really well if you compare to experiments. And this is a slide. This is a picture that I took from this very nice paper from Thomas Suzy and co-workers here, which showed that the model do not really fit experiment. So I'd like you to really for you to focus on the full lines, the red full line. The red full line is exactly the same as the one I showed you for MOS2, but the squared and the red square and the red disk are actually experimental data, and the experimental data do not fit at all on the prediction. This is the same for HBN. You see that the experimental data do not work at all on the prediction of the model I just showed you. But on the other hand, if you look at graphene, the experimental data seem to fit very well. So it looks like it seems maybe there is a problem here when we have semiconductor or insulator. I mean, MOS2 is a semiconductor and HBN is a large gap insulator, while graphene is a semi-metal. So there seems to be really a problem here that we are missing something. And so this is the goal of the rest of this presentation, is to show you what we are missing, and in fact show that by introducing we understand what's going on. So just to make this point even stronger, the gap between the prediction and the value that's shown experimentally for the critical energy of the beam is quite significant. It's more than 100% sometimes. And I just like to be clear, just to summarize, experimentally sputtering happens much sooner than this classical collision model would predict. For those who are really interested in this topic, I invite you to look at the references that I have on the slides. These references are really relevant to understanding this sputtering rate. Okay, now the first question you can ask is, maybe the issue is temperature. All those materials, all those experiments take place at fairly high temperature, certainly room temperature. Even though the model that I showed you are not temperature dependent. In fact, they happen at T equals 0. All those suppose T equals 0. So maybe there is a temperature effect. Well, in the first reference I gave you from Anthony, from my former students in the thesis, he actually studied this, and here is the result that we have. So of course, if you have a depth of a well which is ED, if we turn on the temperature, there will be a vibration of the atom in the well. And we know from the equipartition theorem that there will be some velocity and some energy imparted to the atom. So in other words, the atoms start to vibrate in the well, and potentially it would be easier to actually get it out of the well, because it has some energy itself, either potential energy or kinetic energy, or the sum of the two. Now you can calculate how this affects ED, so the threshold, so how hard it is to remove the atom from the well. You can calculate that as a function of the excitation, the vibration excitations. You see, temperature does not show here simply because the temperature would show in terms of which n are excited through the Bose-Einstein distribution. But this energy fluctuates with time. I mean, the kinetic energy fluctuates with time. And you can actually calculate all these things by looking at time, then the frequency and the excitation number. This is actually not as complicated as it sounds. Again, I invite you to look into the reference if you want. But the point is, you can now modify you can calculate the new cross section by taking into account the distribution of frequencies and the excited vibration as a function of temperature, integrate over time, and then integrate over all the density of state of vibration. Do not be scared about this equation. It's really not very complicated, and I purposely go very quickly on the equations because I want to give you a more intuitive explanation. The point is, this equation takes into account the fact that the atom is vibrating in the well. So this is the idea, and then we can plot this. And in fact, if we plot this, we look at the sputtering rate. Sputtering rate is slightly modified, and the idea is that as opposed to the static crystal, which is the result I showed you so far, the effect of temperature is to smooth things out, to broaden the effect. And it does not account for the huge difference between the prediction and the experiment. And this is not surprising, because of course we always have to keep in mind as physicists and material scientists that the energy scales. When we increase the temperature, the most energy we can expect to impart to the atoms is probably a fraction of electron volt. So we cannot really reduce the critical energy enough to justify increasing the sputtering rate at low temperature. It's just a matter of energy scale. However, the nice thing about this work is that it confirms that experimentally, when you increase the temperature, you do indeed increase the sputtering rate. And in fact, very often, very many papers have reported that it is the combination of temperature effect and energy of the electron beam that can actually allow you to work very closely to the sputtering type that you want to have. So this is good. So this is temperature effect. It's not enough to explain the discrepancy, but it's enough to help a little bit having a full description of sputtering. Okay, so clearly temperature effects cannot account for the discrepancies. So it's time to introduce the last piece of the last piece that we are missing in this description. So the first is, so far what we have looked at is the interaction between the beam electron and the nucleus. One thing that we have completely ignored is the interaction between the beam electron and the electron in the material. So what happens is that when a beam electron interact with the material, it is not just to have a momentum transfer with the nucleus, it's also to excite electrons. So this was the starting hypothesis. So in other words, what we've done so far, we use a McKinley-Feshbach scattering approach, which is basically a momentum transfer between beam electron and nuclei. It turns out we also have to include the interaction between the beam electrons and the material electrons. And when you do that, you find that the bond, so basically the critical energy, the threshold energy, or the strength of the bond is actually weakened and makes it easier to sputter the atoms. So that's what I just told you is the result. I'm just going to explain that to you now. So we are going to look into that into the next 5-10 minutes, and hopefully you will be convinced. Now, the reason why this is difficult is because it's kind of difficult to see what is the interaction between a fast electron moving into a material and the electron themselves. It's really the interaction between the bond electrons and an electromagnetic field, or in this case an electric field, generated by the electron moving. And this is not an easy problem to look at. It's not at all. In fact, it's a problem that has, if you want to solve it correctly, you need to use approaches such as quantum electrodynamics, and it's exactly what we've done. So the fundamental interaction, just to summarize before we move on, is that the beam interacts with the material electrons. We can excite electrons from the ground state to the conduction band. Next, some of those excitations not going to survive because we have a relaxation time, which makes the problem even harder. And at the end of the day, what happened is the displacement threshold is going to be dependent on how many excitations survive. And I'm going to provide you an intuitive idea why that is so. Just hang on and I will show that to you. Now, here's for another equation. Again, nothing to be worried about. This total cross-section, we are starting to do something very nice now, because we started from the rightmost part, d sigma over dE, so essentially the cross-section that we discussed about. Now we basically dress this equation with a probability of excitations, pi, which is the number of initial electronic excitation. Pf is the number that are still there at the end after a certain relaxation time tau. So do not worry too much. What you have to think about, do not think so much of equation if you're not comfortable. Think about the fact that you have your material. The material is going to get a number of electronic excitations due to the interaction with the electron beam. Some of those excitations are going to relax, and the relaxation can be pretty fast. And at the end of the day, what we're interested in is how do the surviving excitation modify the threshold energy. That's basically what this equation does, and we are going to look at that. So the problem is this one. It's really a difficult problem. The problem is, how does an external electron move zipping fast by this atom going to interact with the electrons of the material. So this is where we can use intuition. And in fact, we can always try, as we always try to do when we do theory, try to answer a simpler question and see how we can get to the right answer at the end. So the easier problem is to consider two free electrons. Imagine that you have two free electrons. Do not worry so much about the bond electron for now. So the two free electrons can be described by a plane wave, and they have a momentum P1 and P2. And of course, you will see here the start of a Feynman diagram. The time, the arrow of time is vertical. So the two electrons actually have a momentum P1 and momentum P2. And according to quantum electrodynamics, they're going to interact, have an interaction that's mediated by the exchange of a photon. The photon will have a momentum Q, and the scattering will then result in the electron in the beam and the electron in the material to be scattered in P3 and P4. We do not know which electron is which, of course. We know we are really doing quantum mechanics, but the point remains that you can describe this theoretically, and this Feynman diagram gives us a probability amplitude, which is here. So basically a matrix element, as we have seen, between the incoming electron described by P1, P2, and the outgoing electron described by P3, P4, and this operator is a scattering operator. Now, the good news is that I'm not going to provide you the equation of what T is. We can actually find T, which is going through the electrostatic and electrodynamics, in fact, interaction. Suffices to say that that particular operator can be described by the Feynman diagram. So we can actually solve this problem. And the question is, how do we solve the problem we're interested in? And the problem we're interested in is how we go from free electrons to the interaction of a free electron, if you will, I mean, accelerated electron from the beam, and the bond electron of the material. How do we go from there? So, actually not so complicated. And this is actually probably the key thing that we are going to do now. How do we go from here to there? Okay. It's always a good idea to remember, in quantum mechanics, we always say that in the Dirac notation, it's always a good idea to understand what the bra and the kets are in the matrix element. So we know the brackets, so the matrix element of T on the left-hand side, and we are really interested in the matrix element on the right-hand side. For those who are not familiar with the Dirac notation and so on, do not worry so much. It's just a matter of calculating the integral between the excited state and ground state with a kernel given by T. Now, we always say in introductory quantum mechanics that your best friend is the completeness relationship, and which is expressed usually by the development of the identity in a given basis. Now, the idea, of course, is we can describe, for example, in density functional theory, every single orbital, for example, Cohen-Sham orbital, as a plane wave, as a sum of plane waves. In fact, that's what we do. We do that a lot. We do the sum of plane wave in many cases. Of course, this is the state is not a plane wave, but the state is a superposition of plane wave with different coefficients, and those coefficients are actually calculated in DFT. So let's try to see what that means. That means that if I start from this matrix element and I introduce the identity operator on the full basis of the momenta P1 and P2, I can do that. Then I end up with this integral. And then we are very happy when you see this, because this matrix element is the scattering amplitude of the free electrons. Now, what remains to be calculated are those elements, which are essentially the projection of the ground state on the plane wave basis P1. I mean, the basis of two electrons given by plane wave P1, P2, as well as the excited one. So this is actually the most important contribution we've done to this work, is to be able to do this integral And when you do this integral, which is actually kind of computationally expensive because you have to consider all the possible transition P1, P2 to P3, P4, but it is possible to do. You end up with an equation for any state that looks like this. Complicated equation, yeah, because long and long to write, but truly what I just explained to you in terms of matrix element is exactly what happens. So we can really consider the 4-electron state corresponding interaction with a beam. Now, of course, the problem with this is that we cannot calculate all the elements simply because it's an infinite series and we have to worry about ordering of time and things like that. Well, at the end of the day, if we were able to do it exactly, we would be able to calculate the probability to go from a ground state to an excited state in the presence of an external field, and that will be given by the square modulus of the matrix element. So for those of you who are familiar with elementary quantum mechanics, that shouldn't pose much problem. For the others, do not beat yourself up. This is basically what physicists do. The main thing that you should remember is that we can calculate those interactions using quantum electrodynamics. And in quantum electrodynamics, this is where those Feynman diagram shows. And I purposely did not go into the detail of how we did this, and I invite you to look into the paper if you're interested. But what matters is that there are two basic interactions that matter, and they are in the first order, which is for the T channel and U channel, and they are given by this Feynman diagram. Now, I'm going to go to the next slide and explain a little bit more the Feynman diagram on the left, so that this is something that you have in addition, that you understand a bit more. So in Feynman diagram, we always have an arrow of time, and in this case it's vertical. Sometimes people do it horizontally, but in this case we do it vertically. So that means that initially you have a beam electron and a material electron. Here we actually have spinors because we actually describe the beam electron and material electron by all the quantum numbers that matter, not just the momentum. So it's a four vector, if you will. So include the different properties that you have. These are going to, when you have two line meeting, that means that you have interaction. This interaction is mediated by the exchange of a photon with momentum q, and then you have scattered material. And so you have the before and after. This is really how it works. Now, what happens with the wiggly line? The wiggly line is essentially representing this matrix element that I mentioned before. This is basically everything is in there. Okay. Now it's time to show what we can do. Now, what we can do with this, we can actually now calculate the probability of excitations that we have. And so we can, so essentially remember what we do here, we have electron with a certain energy, or Brownian energy, and we are interested to know how many excitations am I going to have in my material. But that we know because we just calculated the probability. And what we find here is that the number of excitation is actually pretty large. How you excite your material increases significantly. I mean, it's pretty large even at low energy. And we also see that the probability of that there is no excitations, there's no excitations at all, increases as a function of energy. So yeah, that's a little bit surprising, right? You would think the more energy you have, the more excitations you have, but that's not exactly true because, of course, the faster the electrons go, the beam electron goes, the less likely it interacts with the material, just because of the interaction cross section. So you can calculate this for different materials. Remember, we are doing the integral over the excited and ground state, which are, of course, material dependent. And we find that depending on the material we look at, for example, HBN or MOS2, we see the number of excitation is, the numbers of excitations are different. So this is very nice because now we can predict what's the effect of the electron beam on the electronic state. So we can do that pretty accurately. And just to give you an idea of how difficult these calculations are, this is, for example, the band structure of MOS2. We need to consider every single pair of excited and ground electrons not just the vertical interaction, but any of them, like those two that I showed you in the material. That's what makes the calculation a little tedious, but definitely possible. But even though it's a bit tedious, that the calculation is based on the DFT calculation, which is actually not a very expensive calculation. The expensive calculation is to, of course, do the integral. Now, we're still missing one piece. And the piece we are missing is that timescale matters. So timescales matter in the sense that you do have initial excitations, so what we call PI, so the probability of initial excitations. But in many material, the timescale, the lifetime for excitation is very low. And so what really matters is not so much the number of initial excitation. What matters is the number of surviving excitation. So PF is the probability of excitation, final excitation. And we can calculate this again using statistical mechanics. But suffices to say that what matters is the survival rate, which is given by the excitation lifetime tau. So tau is on the denominator on the last equation here. And this excitation lifetime can be measured, can be calculated. So it's a little bit of a complicated calculation. You can do that with time-dependent DFT, for instance. But this is what we are going to use in our model as a free parameter to match with experiment. Okay? So just to stop for 1 second. What we've done, we know the effect of the electron beam on the number of excitation we have in the material, and we know how to calculate the total number of excitations after a certain time. Good. Now you can ask this question is, why does it matter? Why does an excitation, an electronic excitation, matter to the sputtering rate? Well, the reason is, and I'm going to show that to you with two intuitive examples, why the threshold is lowered when you excite the electrons. I'm going to show that to you now. So a stable atom sits in the potential well. We know that. We need to find energy to put it over. Why does an electronic excitation help in this process? Why would it help? Well, this is, when I was preparing for these slides, I was wondering how to present this. There are different ways to do it, different ways to explain, but I decided to go back to the very first problem that we have seen in Huckel theory in quantum chemistry, or even in other courses, and I hope it will be enlightening to you. And this is all about the bond softening. And for that, I'm going to go back to the H2 molecule. And the H2 molecule obtained in the Huckel theory from the basic orbital 1s. And we know there are two ways to combine two 1s electrons in H2. One is symmetric, is in phase, that would be the one at the bottom, the green, or the other one out of phase, completely out of phase, so -1 phase. Then there is an interference between them, or you have two possibilities. And you know what it means, that the density of charge is actually going to be the square of the wave function. So the wave function is what we plotted so far. So on the top, we are going to have a wave function like this. On the bottom, we have a wave function like this. Now we know that the top one is an anti-bonding because there is very little electron density between the hydrogen atoms and therefore no electrostatic screening. And the other one is bonding because the charge is the finite charge, that's actually the probability of finding charge in between the atoms is large enough to screen the repulsion between the positive ion H+. So this is why we have bonding and anti-bonding. And in fact, if you calculate the energies, you find that the energies of the bonding is much lower, is significantly lower than the energy of the anti-bonding. Now, in the ground state, we know that the electrons are going to occupy with two different spin the lower energy. Now, if you excite this, for example, with an electron beam, you see the electron has to move there. This is the first excitation. And this first excitation leads to some electron going from a bonding to an anti-bonding. In other words, you make the bond, or the threshold energy, significantly lower by doing this. So you are softening the bond. And in fact, you can look at different examples. And here I decided to use benzene just because benzene is pretty close to some of the 2D material we're interested in, like graphene. And you see that the crossover between bonding and anti-bonding state makes it clear that if you excite electrons, you make your system much less stable. Still stable, but much less stable. And the energy of the threshold energy goes down. So to summarize, the bond softening is related to doing this. We are basically changing the potential well, the depth of the potential well. And you can calculate that. For those who are into DFT, you can calculate these things so much in a convincing way using constrained DFT. I'm not going to go into that, but you can calculate the threshold energy for sputtering for different material, for different system, as a function number of excitation. And we see that you actually reduce significantly the threshold for sputtering. So the threshold for sputtering comes from the excitation of the electron. Now we can go back to the equation that I've already shown you a couple of times, and now we have all we need in there. We have all we need. And then we can look at the applications. That's going to be the last part of this presentation for the next 2 minutes. So if we look at the edge of HBN, so hexagonal boron nitride, there are a lot of curves on this plot, and I'm sorry, so please just look at the white data. Just ignore the purple and orange one for now. The dashed line is the one that I showed you before, just looking at the normal scattering in the sense of momentum transfer without taking into excitations. If you take into account electronic excitations, you get the full white curve. And the experimental data are shown with the square dot. The fitting parameter here is the time scale of survival, which is about 100 femtoseconds. Now, if you look at MOS2, again, same thing. And again, I'd like to invite you to just look at compare the blue curve, which include excitations, with the white dashed curve, which does not include any excitations at all. I mean, in the scattered system that we looked at before. I mean, the momentum transfer. And again, the experimental data fit amazingly well with the model. I'd like to go even further. Think about graphene. You remember I showed you data that graphene seemed to be the model for graphene. Sputtering in graphene can be very well explained without taking into account excitation. Now we understand why. The lifetime of an excitation in a metal is essentially zero. It's negligible, simply because there are enough electrons around to kill the excitations, if you will. So that means that including the electronic excitation is really important in semiconductor and insulator. One last thing I'd like to talk to you about, I mentioned to you the migration. So the energy for migration, in that case, the difference between what we had before is that the momentum change, the change in momentum for the atom should be in plane so that it's displaced. Again, we can calculate the threshold energy in this situation. Like before I start the movie here, the animation here, I hope you see that we can see here that this is the atom that we are going to displace. There is actually a sulfur atom missing here, and there is a sulfur atom missing here. The idea is that we are going to increase the energy, the initial kinetic energy in the molecular dynamics calculation, until we see this atom moving here. So if the atom moves here, it's going to be a migration. If it doesn't, then we don't have enough energy. Well, you probably already suspect what's going to happen here. In the first case, there is a reorganization, but the atom comes back home. It doesn't get sputtered, it goes back home. Of course, here we do not have all the relaxation effect, but the vibration will actually dissipate across the system, and then you will not have this oscillatory motion. In the other case, the energy is just enough so that the atom ends up in the potential well of the other atoms. You see that the energy for threshold is much lower here. It's 4.5 eV, it's probably 50–60% lower than it is for sputtering. And in fact, if you look at the displacement rate, so the top result, those things here are for migration, and the one at the bottom are for sputtering. You see that the displacement rate is significantly higher. It's at least 1 order of magnitude larger than sputtering rate. So migrating is much easier to migrate atom than it is to sputter. But of course, you can only migrate if you have vacancies already in place, because this is a displacement of a vacancy. So to summarize, we've calculated the cross section. Essentially, what are the parameters that we need to use in order for the electron beam, which is here represented by the arrow, to hit the target? This is what we've done. I hope this presentation was helpful in trying to explain what's going on during sputtering. This is a theoretician's perspective. I try to link this to experiment to show you how we can understand what's happening and explain the different scenarios, and I hope it was convincing. So once again, this is the conclusion and the main paper that explain all this in detail. I have to also say again that the citations that I provided, the references I provided in this presentation, also have looked into this problem before from a different perspective. This is, of course, like in any field, there are many different contributions, and we should make sure that we give credit where it's deserved. This work was funded by the NSF, and the work was done actually at RPI by student Anthony. I thank you very much for your attention. Thank you.